Okay, guys, we're continuing on with our problem of starting our patient on theophylline. So we determined that we were going to be giving our patient either 400 or 350 milligrams of theophylline every 8 hours. Okay, so now we need to determine when to draw We need to determine when to draw concentration information. So how do we decide that? Again, it depends on how critical the patient is, but for the most part, we're really not going to be able to evaluate that CSS with the operative word CSS until we're at CSS. So when does steady state occur? Okay, we already talked about 5 half-lives, so I think his half-life was 8.66 hours. We estimated times 5, which I think worked out to be like 43. I don't remember now. I have to calculate it again. 8.66 times 5. 43.3 hours. So we're going to need to wait at least 2 days, aren't we? So that's our general rule. We're going to wait at least 5 half-lives until we draw a concentration. Otherwise, we're not going to be at steady state. Okay? So, and we can use that on any drug. For the most part, any drug, right? We can make sure they're at steady state. Now comes some interesting stuff. So now we're going to adjust. So let's say we have a concentration drawn 2 days later, and it's like 11 or 12 and a half, just as we had expected. Then we just keep them going on that 400 or 350, whichever it was, every 8 hours. But let's pretend it's not that blissful here. So in this case, what's happening? I'm going to change the color of my, I'm going to be red now. Okay, let's say your patient calls you with complaints of being jittery and their heart racing. These are signs and symptoms of too much theophylline. So remember, the most important thing is look at the patient. Don't just necessarily look at the level. So look at the patient. What's going on with the patient? So you get a blood concentration to see if maybe it's too much theophylline. And your theophylline's on an oral dosing regimen of 400 every 8 hours. So we were going to expecting a CSS average of 12 and a half, right? But guess what it is? It's 22. Almost double. So what went wrong? Well, remember, we were just guessing on his clearance, right? So obviously this patient has much lower clearance than what we guessed because the CSS average is way too high. So we overestimated the clearance. This patient's clearance is actually much slower. So that's what went wrong. So we're going to need to hold, we're going to need to give less, we're going to have to decrease their dose rate, obviously. And we need to know how long we're going to have to hold the theophylline before we start it again. Now, we still want to target 12, so I'm going to just get a clean sheet of paper. So we know that our C target is 12 milligrams per liter still, right? So we need to still get to 12 milligrams per liter. We know that when we were giving 400 milligrams Q8 that we got 22 milligrams per liter. So if we know that, remember, if we know that, we can say, okay, when we're giving 400 milligrams Q8, which we worked out to be 50 milligrams per hour. If you have to do the math quick, go ahead and do that, but we had figured that out before and I remembered it. So we're giving 50 milligrams per hour and we know that the bioavailability is 1 And we know that we ended up with a CSS average of not 12.5 as we predicted, but 22 milligrams per liter. We can calculate what our patient's clearance is, right? So it's going to be 50 divided by 22. And what happens with the units? Milligrams cancel, and we have liters per hour, which is a clearance term, so that's good. So it's going to be 2.27 liters per hour. So this patient's clearance is much slower. Remember, our population said 4 liters per hour. So, but our patient's actual clearance is 2.27 liters per hour. Yikes. Okay, I don't want to erase all, do I? So let's figure out our new dosing regimen to begin with. Well, I should leave that. We know that the patient's clearance is 2.27 liters per hour. We want to know what dose rate we need to give to get a concentration of 12 milligrams per liter, assuming again that our bioavailability is 1. So 2.27 times 12 gives us a dose rate of 27.24 milligrams per hour, right? Because that's hour, milligrams, liters. So yeah, it's in milligrams per hour. So 27.24 times 24. So our daily dose rate is 653.76 per day. Yes? Now, since our clearance is so slow, we could maybe give it twice a day rather than 3 times a day. How would we figure that out? Well, we could figure out a guess of his half-life. I'm going to just leave all this here for now. Got to remember what his clearance was. So half-life is going to be 0.693 volume over clearance, and we know that our patient's clearance is not 4, but closer to 2.27 liters per hour. And his volume, we're going to still have to use our population guess, which is 0.5 liters per kilogram. So we're guessing that he has a volume of 50 liters. So those will cancel and we'll have hours. Good, that's what we want. So let's see. 0.693 times 50 divided by 2.27. So now our half-life is more like 15 hours, 15.26 hours. So yeah, I'm going to change this to Q12 because it's going to be easier for our patient to take it twice a day rather than 3 times a day. So we're going to divide 653.76 in 2, aren't we? 653.76 divided by 2 is 326.88 milligrams Q12. Again, if you can only do 50 milligram increments, we could do 300 or 350 and put those into our equation and decide which one of them we want to have. I think I'm going to do that for you just so you can see the get the experience of doing this again. So we have the choice of, let me erase all of this. $300 milligrams Q12 or 350 milligrams Q12, right? So 300 milligrams Q12 is 600 milligrams per day divided by 24 hours. So 300 is, wait, I don't know if you can that go away a little bit? Well, is 25 milligrams per hour. And 350 divided by 24 is, that can't be right. 300 divided by 24, 12 and a half. What did I do? No, that's right. 600 divided by 24 is 25. Sorry, I'm getting all turned around here. Or 350 times 2 divided by 24 is 29.17 milligrams per hour. So what do we expect to see for our CSS average with each of those? Now that we know that our clearance is closer to 2 rather than 4 liters per hour. So CSS average is going to be equal to bioavailable dose rate, so 25 milligrams per hour divided by 2.27 liters per hour. So let's see, hours, milligrams per liter. Yep, that's what we want. So 25, and remember our bioavailability is 1. If it was anything but 1, we'd have to be doing that, taking care of that in our algebraic calculations as well. So if we give 25 milligrams per hour, we'll expect a concentration of 11 milligrams per liter about. And if we give 29.17 milligrams per hour divided by 2.27, we're going to expect about 12.85, so I'm going to say about 13 milligrams per liter. So let the team decide which one of those you're going to choose, either 300 milligrams Q12 or 350 Q12. But you can tell them at 300 milligrams Q12 they're going to have a CSS average of around 11, and at 350 it'll be around 13. Does everybody see how to do that? Good. Now, we didn't really need to figure out the clearance, although it is helpful to figure out the clearance because you can then figure out the half-life. We could have said, right, that CSS average is equal to bioavailable dose rate all over clearance, that if these two stay the same, if we have no reason to think that those will change, then CSS average and dose rate become proportional, don't they? So we could say at dose rate 1, we're going to get CSS average 1, and that should be equal to dose rate 2, as is to CSS average 2, right? So our dose rate 1, we gave what? 400 milligrams Q8, so that is 1200 milligrams per day, and our resulting CSS average was 22 milligrams per liter. This was given to us, right? And they were having toxic side effects, so that's too much. We know we have to give less, don't we? So what's our new dose rate going to be that we're going to suggest if we're shooting for a concentration of 12 milligrams per liter? So now we just set up a simple proportion, don't we? And I will tell you it will come out the same as when we did the other, but let's go ahead and do it. Or it should at least. So this new dose rate is the exact same as we had before, 654 milligrams per day. And again, if we divide that into 654 divided by 24, so that's about 27 milligrams per hour. So we're in the same pickle, right, as we were before. This recommends 327 milligrams Q12 hours. So again, we could go back in and decide if we want to give 300 or 350 every 12 hours. And another way you could do that is by now we use a proportion and say, okay, if we give 300 milligrams Q12, right? 300 times 2 divided by 24, that's 25. Well, let's just do it by day. This is in days. Whoops, this is in days, isn't it? Sorry, should have read my units. This is why units are important. So if we're giving 300 Q12, that's easy. We're going to give 600 milligrams Q day. And then we solve for our CSS average, don't we? So 600 times 22 divided by 1200. So X is 11 milligrams per liter, just what we got before. Right? So at 300 milligrams, we're going to get a CSS of about 11 milligrams per liter. If we give 350 milligrams Q12, then this changes to 700 milligrams a day, right? So 700 times 22 divided by 1200. So the X is 12.8. So that same thing we got before, about 13 milligrams per liter. So those are your choices, just like we said before. Okay, so we're going to either recommend 300 or 350 milligrams every 12 hours for our patient. Now the next part of the question is, how long do we hold the dose? This is a little trickier, isn't it? So if we know right now that we're at 22 milligrams per liter, and we want to know when it gets down to 12, because then we can start our drug again. We're holding the dose, so the drug is decaying, isn't it, if this is natural log concentration. So we want to know what this time difference is, don't we? This is a decay model, one compartment decay model, so we can use our good old CT is equal to C0 e to the negative KT. Right? So if that's the case, then we know that C0 here is 22, don't we? Milligrams per liter. And where we want to get to is 12 milligrams per liter. So our CT is 12 milligrams per liter. And the T here is going to be the time difference between those. That's what we're solving for here. What's our K going to be? Well, we just determined our clearance is equal to 2.27 liters per hour. And we're still guessing that the volume is about 50 liters. So what's our K going to be? It's going to be 2.27 divided by 50, right? If we, let's check our units. Liters cancel. It's going to be per hour. That's what we want, right? So 2.27 divided by 50. So our K is going to be 0.045. You can put the other 4 on there if you want, per hour. Okay, so then we need to come in here and solve. Solve. Oops, erase. Our K is going to be 0.045 per hour. And now we're solving for T. Do you all know how to do the algebra to do this? First thing I do, this is also milligrams per liter. So 12 divided, so bring 22 over. So we have to divide by 22. So 12 divided by 22 is 0.545. This is milligrams per liter. Equals e to the negative 0.045 times t. Now how do we get rid of this e? Well, we natural log each side, don't we? So what's the natural log of 0.545? Okay, I'm going to have to erase some here because I'm running out of room. So the natural log is minus 0.06, oops, sorry, 0.606 equals minus 0.045 t per hour. Okay? So now we have to divide this side by minus 0.045, don't we, to get t. Divided by 0.045. Make sure it's the minus because it needs to be plus. Our time can't be in negative hours. So our t will be 13.47. So we're going to need to wait at least 13.5 hours to start it again. So I might round that to 12 just because that's a more reasonable number, but you're going to need about 13.5. If I ask you on an exam, do the exact number, or if I ask you what you would round it to, I would round that to 12. So I would hold it for 12 hours and then start your Q12 either 300 or 350 every 12 hours of theophylline. Okay? That's it for this one.